Okay, let's get started, please. First off, how many of you know what Pascal's triangle is? Pascal's triangle? Can somebody tell me what Pascal's triangle is? Yeah, when?
Isn't it like it's the triangle you start off with 1,
Yeah.
and you go 1,
1,
and then 1,
1,
2,
2,
1,
1, yeah.
and you keep
1,
going
3, 1. So you have ones on the outsides, you have ones on the outsides, and then each of the inside guys is obtained by adding the two guys above it, right? So here I've got 1, and here I'm going to have 4. Here I'm going to have 6, 4, 1, right? 1, 5, 10, 10, 5, 1, etc., etc. Okay, so this is Pascal's, so-called Pascal's triangle. What's it good for? Anything? What?
Finding coefficients.
Finding coefficients, yeah. So coefficients of, if you have something like a plus b to the n, okay, if you have a plus b to the, say, if you have a plus b to the 1, well, that's just a plus b. A plus b squared is going to be a squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, and so on and so forth, right? And you see that the coefficients here, right, there's 1, right, there are 1s here, right? The coefficients 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc., etc. The coefficients turn out to be the same, and these are related to something called choose, like the number of ways you can choose n. You can choose like the number of ways to choose k things from a set of n, right? The number of ways you can choose k things from a set of n. In fact, it turns out that these guys are this is 2 choose 0, 2 choose 1, 2 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, etc., etc. So it has something to do with probabilities, like the number of ways, well, at least combinations, the number of ways that you can choose, a number of elements from a set of other other elements. Don't worry about this choose interpretation, but we'll use Pascal's triangle a little bit in what we're going to do today. Okay. So last time we were talking about, we were in section 3.1, instantaneous rate of change. Okay. And we said that, well, if P of t is the position on a linear track, say, at time t, position at time t. Okay. So if P of t is position at time t, then P of t plus h minus P of t over t plus h minus t is going to be the average rate of change of position over this time period. T plus h. The average rate of change of position with respect to time, so the change of position with respect to time over this time period. Right? So it's the average speed over the time period, and then we did this thing taking the limit the limit as h goes to 0 of this thing. So maybe the cleanest way to say this is average speed over t plus h. No, I should say average velocity. Average velocity. Because speed is usually taken to be a positive number, and this could be a negative number. Noor.
What does it say after?
Period.
Time period.
Yeah, time period. Okay. And then this thing is the instantaneous rate of change. Of position with respect to time at time t, or again, instantaneous velocity. At time t. And we also mentioned that there's this sort of graphical interpretation, right? If this is your p of t, right, then if this is let's say t0, this point is t0. If I look at the limit of p of t0 plus h minus p of t0 over h as h goes to 0, that gives me the slope of the tangent line. At time t0. Right. Each of these guys was the slope subsecant. Each of those guys was the slope of a secant line, and then you take the limit of the slopes of the secant line, and you get the slope of the tangent line. That's basically what we did last time. Yeah, Luke.
What is that word next to time?
Instantaneous? Oh, wait, no. Where?
The middle one.
This one?
With
Yeah.
respect to?
Period?
Period.
Time period. I guess it looks like P naught. Sorry, I should dot the I. I should separate them. Any other questions about my handwriting? I used to have good handwriting. I'm sorry. I should try harder about it. I'm getting lazy with my handwriting. I can tell it's sliding. You know, after you get tenure, you can no longer be fired, and I think it just results in this slippery slope towards corruption. So yeah. Okay. Okay. Questions? Okay. Right. We did this, right? You know, each of these things, right? If I look at T naught plus H, I take this thing, then this thing is the slope of the secant line through those 2 points. I let H go to 0. I get the limit of these slopes as the time period gets shorter and shorter, and that gives me the slope. Ultimately, that gives me the slope of this line called the tangent line. Everyone all right? Okay, so just for practice, let's just do one. The function is x to the 6th, right? And I'd like to know the slope. So it looks sort of like x squared, but more curved. So there would be a point 2 to the 6th, right? What's the slope of the tangent line? What's the slope of the tangent line? At that point. Okay. Take 1 minute and see if you can set it up. And if you can get anywhere, that's great. But if you can't, I just want you to set it up. how do you figure out the slope of the tangent line? Well, you got to use this thing here. Okay, turn to somebody nearby and say what you got.
For P.
Sorry.
And then did you put 2 here? Or 2 to 6?
Well, you don't know what P is right. So,
I don't think it's.
Okay. Okay. So I'm going to do this in a slightly more general way than probably you did it. Okay. So I'm going to look at not just at 2, but at some point x. Okay. And I'm going to say, how would I figure out the slope at that point x? Okay. Well, to figure out the slope of the point x, you need to look at the limit of the slopes of the secant lines. Okay. So this is going to be the limit of x plus h to the 6th minus x to the 6th over h as h goes to 0. Right? My function was the x to the 6th function. Right? So that's what I get. Right? And then h goes to 0. What do I get? X plus h to the 6th. Well, you could use Pascal's triangle, right? Remember the last line that we had was 1, 5, 10, 10, 5, 1. The next one is 1, 10, 1, 6, 15, 20, 15, 6, 1. And those are going to be the coefficients for us. So it'll be x to the 6th plus 6, x to the 5, h plus 15, x to the 4, h squared plus 20, x to the 3, h cubed plus 15, x squared, h to the 4, plus 6, x, h to the 5th, plus h to the 6th, and then minus x to the 6th. Everything over h. Anyway, the coefficients are 1, 6, 15, 20, 15, 6, 1. Via Pascal's triangle. Okay, so yeah, Nico.
Why can't you say, like as h approaches 0, it's just going to be x to the 6th?
Well, you've got x to the 6 over h, right? So as h goes to 0, what happens to that?
What do you mean, which hex? The top one? I mean, like before you like instead of multiplying it out, like, why can't you say like h is going to 0, so x plus h to the 6th is going to be more like x to the 6th?
So you get 0 on the top,
Well, I mean, yeah.
and then you get the 0 on the bottom. Yeah, you could say it, but you see that you run into problems if you start thinking like that. Right. Okay. Yeah. So yeah, I mean, it's not exactly that. That's not exactly what happens. Okay. So let's see exactly what happens. 6x h to the 5th plus h to the 6th. That's the last stress. Okay. So what happens, right? Then thankfully, the x to the 6's cancel each other off, right? And then you end up with the limit as h goes to 0 of right, 6. Well, does anyone see what happens? You've got 1h here, right? So that's just going to cancel off, right? 6x to the 5th, right? You've got 15x to the 4th h squared, so that's going to be 15x 4th h. Right? The powers of h are all going to drop by 1, right? Plus h to the 5th. Right? You divide the top by h, so all the powers of h drop by 1. Right? And you see what happens? As h goes to 0, what happens?
6x5 to the 5th is the only thing left.
Right. Everything else vanishes. Right? All these other terms vanish. So you get 6x to the 5th.
And how do they vanish? Sorry.
Well, because h is going to 0, right? H is going to 0. These guys all involve h. So it's 15x to the 4th times h. As h goes to 0, that dies. This guy, it's going to be h to the 5th. As h goes to 0, that dies. Okay. Yeah, Noor.
Why can't you just not do any of that?
Yeah, how?
I mean, like, because if you know h is going to 0,
Yeah.
like, you have to fill out all those terms.
Well, right. So if you're smart, you say, I know that everything past here, I know that all these guys involve powers of h that are bigger than 2. So, and when I divide by h at the end, when I divide by h, these guys are all going to have powers of h, and so when h goes to 0, it's all going to vanish. Okay. So if you're smart, you sort of stop here and say, and some other terms that are going to vanish. Okay. Right. And then the x to the 6 and the x to the 6 cancel off, and you get left with this thing.
So that's okay if you write it like that?
Well, you see, so what if, okay, so what if we were doing x plus h to the 1,000? Okay, right. What if you're doing x plus h to the 1,000? Marcella, you.
But can't you take the derivative of the original? Like, that's the derivative of x to the 6.
Yes.
Are we not allowed to do that?
This is how you know it. This is how you know it, right? So you don't, how do you know that the derivative, which we haven't talked about yet, is going to be 6x to the 5th? the reason you know it is because of what we're doing right now.
Okay.
Right? So you can't say, oh, I know that the derivative is this because this is what's showing that the derivative is this. Okay. Yeah, when
Will we be ever allowed to use power rule at some point?
you will in a few seconds.
See.
You will in a few seconds. Okay. So, so you're all wanting to. Those of you who've seen calculus before are like, use the power rule. Use the power rule. This is how we get the power rule. This is. Otherwise, you don't know why you can use the power rule, right? This is what justifies the power rule. Pascal's triangle. Okay. Okay. So if I said x plus h to the 1,000, right? Then Nora was saying, oh my God, I don't want to write out Pascal's triangle, 1,000 rows of Pascal's triangle, blah blah blah. Right? That's fair, right? Because you'd have to do so. If we had, say, your function was f of x to the 1,000, then to find the slope, right, you'd have to do this sort of thing, right? As h goes to 0. Right? Okay. But fortunately, you know Pascal's triangle, right? You know what's going to happen, right? It's going to be x to the 1,000 plus what? What's going to be the next term? What's going to be the coefficient? 1,000 x to the 999 h, if you know Pascal's triangle, right? Then plus a bunch of terms, terms involving h to the n, where n is bigger than 2, bigger than or equal to 2. Right? There's going to be h squared, h cubed, h right? X to the 998 times x squared, x to the 997 times h cubed, blah, blah, blah. So terms involving h to the n, where n is bigger than 2. Okay. And then we subtract off the x to the 1,000 and divide by h. Right? What happens? The x to the 1,000 and x to the 1,000 cancel off, and you end up with the limit of h going to 0, x 1,000 x to the 999 plus terms involving h to the n, where n is bigger than 1. Right? Because these guys were all n bigger than 2, n bigger than or equal to 2, and you divide it by h. Now they're terms involving n, h to the n, where n is bigger than or equal to 1. Okay. So what happens is those guys all vanish, and you get 1,000 x to the 999. Okay, and right, if I had f of x, x to the n, right, where n is some natural number, then the same thing's going to happen, right? I'll get the limit of slope at x is going to be the limit of x plus h to the n minus x to the n over h as h goes to 0. And then you see what's going to happen, right? It's going to be x to the n plus n x to the n minus 1 h plus terms. Over h, and I need to subtract off, again, the x to the n. Again, the x to the n's cancel off, and you see what happens. I get n x to the n minus 1. Okay, so coming back to our original question, right? We have x to the 6th at point 2, right? So the slope here, right? Slope here is 6x to the 5th at x equals 2. Right, so it's 6 times 2 to the 5th. That's 192. So you know the slope there. If and at this point I wasn't planning to do this, but sort of pressed on by the class. Yeah. You okay?
Yeah, I'm good.
Okay. So if I gave you another one, say we look at x to the 5th, say at 1. And I say, what's the slope? What's the slope there? What's the slope of the tangent line? What's the slope of the tangent line there? Isaac. 5, right? Because you know that the slope is going to be 5x to the 4th, right? The slope of x to the n is n x to the n minus 1, right? So it's going to be 5x to the 4, 5x to the 5 minus 1, which is 4, right? At x equals 1, so it's going to be slope 5 there. Okay. So this gives you, what we've worked out here is a nice way of, you can get the slopes of slope of the tangent line to any monomial. And from there to any polynomial. But let's hold on for a second. Okay. Okay, at this point I really want to define the word derivative. Okay, so definition. If the limit of f of x plus h minus f of x over h as h approaches 0 exists and is finite, we call this f of x, no, sorry, we call this f prime x. Okay, we call this thing f prime x. The derivative of f at x. And we call f prime, the function f prime, the derivative of f. Okay, and what we've just shown, what we showed here, is that something called the power rule. If f of x is x to the n for some natural number n, then the derivative is n x to the n minus 1. So what we said, if f of x is x to the 6th, then f prime x is 6x to the 5. That was one example. If f of x is x cubed, then f prime x is 3x squared. Okay. And these guys have various interpretations, right? You can think of this as the instantaneous rate of change of f, right? F prime x can be thought of as the instantaneous rate of change of f at x. It can also be thought of as the slope of the tangent line to the graph of f at x, f of x. So we call, I should say, we call this limit. Call this limit f prime x. Okay. I should say one more. No, let me hold on. Okay, any questions at this point? Any questions at this point? So, right, we were talking about instantaneous rate of change. We're talking about instantaneous rate of change, right? It's this thing. Turns out that we actually call this thing the derivative of the function. And just now we worked out that if the function looks like this, then the derivative is easily calculated. Right? It's going to be n x to the n minus 1. Let me do another example of a derivative, another important example. If f of x is the sine function, sine x, and you want to calculate the derivative of it, well, the derivative is going to be the limit of sine x plus h minus sine x over h as h goes to 0. Okay. And so you get, well, you can use the addition formula. Sine x cosine h plus cosine x sine h minus sine x over h as h goes to 0. From here, you can say, well, that equals the limit as h goes to 0 of sine x. So I'm going to take the terms that have sine x on them. Cosine h minus 1 over h. And then I have this other term, cosine x times sine h over h. Is everyone okay with that move? Right. I just took the terms involving sine x, I put them together. I have the left over. I have a term involving cosine x. Okay. So this limit. Does anyone know what happens to this limit? I think it was this was in the book, but we didn't go over it in class.
Well, cosine of 0 would be 1, and so you would get 0.
Yeah, you get.
And that would cancel out the sine x.
Yeah, so it's a little bit more subtle than that, because you see that this goes to the cosine h goes to 1, so the top is going to 0. Okay, but the trouble is that the bottom is also going to 0. Okay, but it turns out that this thing turns into 0. Okay, this thing goes into 0. You can look back in the squeeze theorem section. It's actually this is one of the things in the squeeze theorem section. What about this one? Well, sine h over h, we actually saw this one in the squeeze theorem section. This one goes to 1. Right? this one goes to 1. And so what you end up with is cosine x. So if you have the sine function, it's funny, right? If you have the sine function, and you're interested in the slopes of the sine function, well, the slope of the sine function here is going to be cosine of that, right? So if this is x, right, the height is sine x, and the slope of that is going to be cosine x. Okay, right? At the top, right, at this point here, right, at pi over 2, sine is 0, right? Cosine is 1 there. I'm sorry, sine is 1, cosine is 0. Sorry, I said it backwards. Right, and so on and so forth. Right? They sort of complement each other. One that we're not going to do is another example. One that we're not going to do is what happens to the cosine. It turns out if you take the derivative of the cosine and work it out, who does it? You get negative the sine. Negative the sine. Okay. Everyone following? Anyone lost at this point? Close your eyes for a second. Raise a finger if you're lost. Okay, open your eyes, please. So nobody says they're really lost. There are a couple people who say they might be starting to get lost, or they might be a little bit lost. So, don't worry. It's all we're doing is this, right? You have some function. F is a function, right? And then we create this new function. Create a new function. F prime. Okay. And the way it's defined is f prime at some point is defined to be the limit of f of x plus h minus f of x over h as h goes to 0. Okay. And that function is called that f prime is called the derivative of f. That new function is called the derivative of f. Okay. And what it tells you is, if you, it tells you the slope of the tangent line. Right? F prime x is the slope of the tangent line. That's basically all we've done. Let me give some non-example. Okay. If we look at, for example, the absolute value function, and I say, what's the slope of the tangent line at 0? What's the slope of the tangent line at 0? What do you say to that? What's the slope of the tangent line at 0? Well, it's sort of problematic, right? You want the limit of f of x plus h minus f of x over h as h approaches 0. So that's the limit of the absolute value of x plus h minus the absolute value of x over h as h approaches 0, right, for at h. Right, so you want the limit of the slopes of the secant lines. Okay, why is that a problem? Does anyone see that this is going to be a big problem? Why? Sarah?
Because there's there's more than one
Yeah.
slope.
There's more than
at which
one.
it would only
Yeah,
be
there's more
one
than
point.
exactly. There's more than one possibility here, right? So like if I'm looking at secant lines, right? Here's my 0, 0 plus h, and I look at the slope of the secant line. What's the slope of the secant line? 1, right? So I say, oh, the slope of the secant lines are all 1. As I take the limit of these guys, the limit is 1, right? But if I look at the secant lines here, 0 plus h is negative, say, right? If h is a negative number, then I'm looking at the slopes of these lines. Well, the slopes of these lines are all negative 1, right? And so the trouble is that the limit does not exist. Limit doesn't agree between left and right. Between its left side and right side. Between its left and right sides. Right, so doesn't exist. Doesn't exist. Right, the limit doesn't exist. Okay, so for this guy, we say there's no derivative at that point. Okay, there's no derivative at that point. We say it's not. This function is not differentiable at 0. Right, there's no derivative at x equals 0. Okay. Okay. You could have also some crazy function like sine 1 over x, right? Right, sine 1 over x at x equals 0. Right. Away from x equals 0, it's actually possible. Right. Away from x equals 0, well, look, if I take some point out here, well, I can find tangent lines. Right. I can find tangent lines. Even in here, if I zoom in far enough, I can find some tangent line. But at 0 itself, right? At 0 itself, I'm in trouble, right? Because the thing is going crazy. Right? So like, suppose I'm sorry, I should say 0 at x equals 0. So the function actually wasn't even defined at 0, so I need to give it a definition there. Suppose I call that thing 0. But I'm never going to find the slope of the secant lines because they go crazy, right? They're going up and down and up and down and up and down, right? From negative infinity to positive infinity, all over the place. Right? So this guy's also not non-differentiable. At x equals 0. Okay, I think I was going to do something else, but I think I'll just say one more thing. No, I'll say two more things. 2 remarks. The first one is an easy one. So first is, some people will write, there are various notations for the derivative of f at c. Okay, so the derivative of the function at some point c, the one that we're using is this one, right? F prime of c. Okay, but you also see people write this sort of thing, df dx at c. Okay, df dx at c, or pretty similar, ddx of f at c, or df dx evaluated at x equals c, or derivative of f at c. Anyway, these are all the same thing. Okay, the second remark is that if we look at this thing, f of, let me write it this way, f of c plus h minus f of c over h as h approaches 0, right? This is the derivative at c. Okay. So that you have some point c, you look at c plus h, right? You let the h go to 0. This could also be written as the limit of f of x minus f of c over x minus c as x approaches c. Right, let me make this up. C plus h minus c. So I'm writing, all I want to point out is that these two things are exactly the same, right? The limit, the picture is like this. This is c, and this is x, right? I'm taking the limit of f of x minus f of c as x goes to c, right? Or I'm talking about the limit of f of c plus h minus f of c as h goes to 0, right? But as h goes to 0, x goes to c. Right? These are exactly the same thing. It's like calling me by one name, and calling me by my English name, and calling me by my Chinese name. Right? It's the same person. Yeah, Reina, you have a question?
Oh, no.
Okay. Everyone okay with that? That these two are exactly the same thing. So if we look, sometimes when we're talking about the derivative, we'll use this expression. Sometimes we'll use this expression. Yeah, Win.
I had a question about the homework.
Yeah.
Were we supposed to turn in 3.1 today too?
Nope, no 3.1 today. So 3.1 will be due next time.